sources in series. So there's two things to do. First, let's look at the left one. The left, we have a voltage source, and then we have two different current sources, and they're all in series. This is not okay. This doesn't work. So why? Let's think about this. Conceptually, what a current source is saying is, I have a given amount of current going in this direction. So if we look at the 6 amp current source, it says, I have 6 amps going in this direction. And remember, the only way we can divide current down is if we have a branch, because essentially the sum of the currents going into a point equals the sum of the currents coming out of a point. So if we make the point right where that little bomb is, right on the corner there, that says that 6 amps out equals 4 amps out, which doesn't make sense. You can't have 6 amps equals 4 amps. 6 doesn't equal 4 ever. So this one is not a circuit that we can solve. It's an incorrect circuit. So, and this is mainly because of, well, one, these are ideal sources that we're looking at in this one, and ideally, mathematically, they don't work out. And then two, because of Kirchhoff's current laws, because of that ideal source, if you make a node in between those two, they don't equal each other. So mathematically, you can't do this. Don't. It's wrong if you do. It'll break your math and everything else. It won't work. However, if we look on the right-hand side, we have combining voltage sources. Now that is something we can do. So in that picture A right there, we have a V1, a voltage source, and then a resistor 1, and then a voltage source 2, and then a resistor, and then a voltage source 3. And those V1 and V2 are going in the opposite direction, but V3 is going in the same as V1. So what does this mean? So as we've said before, it doesn't matter which comes first. You can, since they're all in series, voltage sources and resistors, if they're in series, you can reorder them. So to reorder them, I can pull all the voltages over on the left and all the resistors over on the right and take the sum of them. So I can do V1 minus V2. Remember, it's minus V2 because the plus is going in the opposite direction as V1. And then we have V3, which is a plus again because it's going in the same direction. And so that's our V equivalent, and we can plug that into that bottom circuit there, and that's essentially the equivalent circuit for all the voltages. And same with the resistors, because it doesn't matter if R1 comes before R2 or R2 becomes before R1 for this system. We can collect them up, and we can put them in the bottom and add the two because they're in series, and that's going to give us our equivalent circuit, R equivalent. And so redrawing that circuit of 3 different voltage sources and 2 different resistors, we can redraw that as 1 equivalent voltage source and 1 equivalent resistance. So that's one of the ways of simplifying things out. Now, if there is a test probe put right around R1 and it says, what is the voltage before R1 and after R1? Now the order does matter because essentially we're coming from the source. It might be, let's just say we have a 2-volt drop on there. The 2-volt drop doesn't matter. It will always be a 2-volt drop wherever it's located. But if you're going down, let's just say it's a 24-volt source and you have a 2-volt drop. From there, now we've got a 24 minus 2, 22-volt drop, 22 volts after that resistor. So just to keep that in mind, I don't want to confuse you, but when we're trying to simplify these out, we simplify them out as doing V equal or the equivalent voltage and the R equivalent. And this also lets us do our V equals IR really, really easy. So what's the current of this? V equals IR. So the voltage divided by the resistance is going to equal the current. So that's how we solve these. Transformation. And this can be useful sometimes in solving a couple different sets of problems, and also it's just a good tip to know as well. So it can be a shortcut. We're going to learn it, we're going to get through it, and we're going to show you some examples next on the next slide of actually how to use it. So what is it? Source transformation. So let's just say you have the picture up in the top right with picture A, which has a voltage source, then a resistor after that, and some circuit. Again, like we said, that external circuit can be whatever. It's a black box. We don't really care about it as long as it has the same properties. And those properties right now are generated by V12, or the voltage drop across that circuit. So we're going to ignore everything to the right of V12 because, again, this could be any circuit. This could be something really complex. This could be a single resistor, whatever. So we're going to look to the left of that. So in this, we have a voltage source, Vs, and a resistor, R1, and then we have a current coming through out of that voltage source through that resistor and into the external circuit. So, cool thing about source transformation, we can change a voltage source into a current source. And that comes again from Ohm's law. It's another use of Ohm's law because V equals IR. If you lock R down, V equals IR, so you can change from current to voltage. And the essentially you can think of it as the way you change is through the resistance. So what you can do is in the bottom right you have picture B. That's a current source with a resistor in parallel to it. And if that resistor is the exact same resistance as R1, then you have the other equation underneath there, IS equals VS over R1. And so you can actually change one of these, and it works in reverse too. If you have a current source, you can change it back to a voltage source. So sometimes I prefer solving a lot of circuits with a voltage source coming through because it makes it really easy to do Kirchhoff's voltage laws and go right around the loop and it's done. Sometimes it's easier to solve the current source and use the current to solve the equation because maybe the current you're looking for is far away from the voltage source or the source of current. So this sounds a little confusing now. We're going to run through an example or two of it next, and that way we can kind of lock out some of the details and lock it down. So in general, the concept from this slide that I want you to remember is a voltage source with a resistor after it can be changed into a current source with a resistor in parallel. And likewise, a current source with a resistor in parallel can be changed to a voltage source with a resistor in series. So let's look in the next slide and do a couple different examples of this and see if we can lock it down.